But to get started, let's look at the data. This is the NASA 136 years of land and ocean surface temperature. You see every year playing out before you. Notice that from one spot to the next, there's not a consistent temperature change. Notice that from 1 year to the next, there's not consistent temperature change. But also notice that overall, through this 137 years, there's clear warming that has taken place. And you can also see that the Arctic has warmed faster than anywhere else. This is called Arctic amplification. And I'm going to return to that problem in a little bit to explain the terrible weather disasters that we've been having, the dramatic heat waves, the dramatic rainfall, and the intense snowstorms that happened. The same data plotted since 1880, year by year. Again, you can see periods of stability where we have several years to decades without strongly changing global temperature. Then we have a couple of years to a decade or two of warming temperature, stability, warming. We had about a decade and a half of stable climate, and now we're warming again. And we'll hear in the next week or two what the temperature was for this past year, 2016, but the prediction is that it's up here. 2014 was a record-breaking year. 2015 broke that record by 20%, which we've never seen one year break another year by that much. And 2016 looks like it's poised to be a dramatically warmer year as well. We think that this sort of stair-step behavior of the temperature is related to processes in the Pacific Ocean. The Pacific Ocean, it turns out, absorbs heat from the air, and so around the world, it's a cool year. And the Pacific Ocean can release heat into the air, and around the world, it will be a hot year. El Nino and La Nina do this, and we'll be talking about those processes. But there's another process called the Pacific Decadal Oscillation, and as the word implies, it's decadal. El Nino and La Nina come and go on the timescale of years, but these stable decades and unstable decades of rapid change are basically an El Nino and La Nina process played out over decades, where for a long period of time the ocean will absorb heat and stabilize temperature, and then for another decade or two it will release heat and cause this rapid warming to take place. This is from NASA. What you're looking at is the carbon dioxide on the planet. The blue colors are relatively low levels of carbon dioxide. The warm colors, notice they're largely in the northern hemisphere, are excessive amounts of carbon dioxide. And CO2 is the most dangerous greenhouse gas because once it's up in the air, half of it will stay there for centuries to over 1,000 years. As we release CO2, for every time you drive your car and CO2 comes out of your tailpipe, 25% of it will be absorbed in the ocean. That's at a cost because it turns ocean water, it acidifies ocean water. And 25% of it will be recycled through the photosynthetic cycles, the biosphere. But 50% of it will stay in the air and stay there for centuries to thousands of years. So the climate change that the CO2 we have already released, that climate change is not going to stop when we decide to drive electric vehicles and turn off our coal power plants. We are in for permanent climate change from the human point of view. And so we have to adapt to the impacts that this essentially permanent climate change is bringing to us. I wanted to take you back a little bit into geologic history. What we're looking at here is 400,000 years of ice ages where this line goes down and warm periods where the line comes up. And this is carbon dioxide concentration on the planet that we get from ice cores in Antarctica. We can core through 2 kilometers of ice in Antarctica, and we get very high resolution record of the CO2 at the time, and we can also get temperature from this record as well. Because of how the Earth and the Sun change their orientation, we drive a natural climate pattern involving ice ages and warm periods every 100,000 years. Earth's axis is tilted, that gives us our seasons, but the tilt isn't stable. We tilt a little bit more and a little bit away from the sun. The axis also wobbles in the sky, and our orbit around the sun goes from more circular to more eccentric and back to more circular. That is a 100,000-year process. This is a 40,000-year process, and this is a 20,000-year process. And all of those modulate the sunlight that hits 60 degrees north latitude, where you have the most land. That land, if you have short, cool summers, can accumulate snow from one year to the next and reflect more and more sunlight, causing a feedback process that drives you into an ice age. If you tilt away from the sun and you happen to be at an eccentric point when it's summertime in the northern hemisphere, you can have a long, warm summer. That kickstarts the retreat out of an ice age. It leads to melting of all the snow, and we go into an interglacial. So the multiple cycles lead to this, what looks like just a random line, but it's not random at all. It's mathematically correlated to these astronomical parameters. So let's come a little bit closer in time. Here we are 24,000 years ago up to present day. We have an ice age. We have the current interglacial that we live in. The last ice age, and I'm sure you've seen Ice Age 1, 2, and 3. We're all experts on Ice Age. Ended around 18,000 years ago. It culminated about 10,000 years ago. This is the time where that very kind climate allowed for domestication of animals, learning how to grow crops, a lot of deforestation, and we developed our first cities and our villages, all during this period of time known as the Holocene, which stands for recent time. Notice the gentle curve down as we go into the end of the Holocene. We were headed down into our next ice age. Again, a direction that is controlled by the geometry of the gravitational field of the Earth and the Sun. Papers just recently came out stating that they've calculated that we're going to miss the next ice age. We will completely miss the next ice age because we've captured climate on this planet. This is one of the stunning aspects of climate change that just really set me back on my heels. This multi-million year pattern of Earth climate is now disrupted by the fact that we've dumped so much CO2 into the atmosphere. And here you can see the red, it is the temperature that is projected to occur as we move forward over the course of this century. Last December, or a year ago December in Paris, 2015, the world's nations came together and agreed to stop climate change at 2 degrees C, and everybody has made promises for how they're going to cut back on their greenhouse gas emissions. Well, it turns out if we want to stop at 2 degrees C, we need to stop burning carbon this year, which of course is not going to happen. Right now, renewable energy makes up about 10% of the global planet source of energy. So we're not anywhere near 100% renewable energy or low carbon energy. At 3 degrees C, which our current greenhouse gas emissions are going to give us, large areas of the planet can't support human life, can't support human activity. You simply cannot go outside and work for the day because the air temperature will be too hot for your body to offload heat. If you can't work, you can't live in an area. You can't farm, you can't do other things. And so we're going to see big tracts of the Middle East, North Africa, Latin America. These areas are going to become too hot to live in. And of course, that's going to be stimulating human migration, waves of human migration, something we need to wrestle with. At 4 degrees C, which with our current track of releasing greenhouse gases, we will arrive around 2075. So on the order of 60 years from now. We'll have set Greenland and Antarctica onto an unstoppable melt path. And in fact, I'm going to show you that parts of Antarctica are already on an unstoppable melt. Once you begin to lower the plateau on one of these huge ice sheets, it triggers a feedback process, because as you lower, you're just going into warmer air. You're moving towards the rain zone and out of the snow zone. And there's nothing we can do to stop it, because we can't change the temperature of the planet unless we geoengineer it. And the Obama administration, just this morning, maybe it was yesterday, sent out a message asking that more research be done on geoengineering. So that is something that we're going to be looking at in the coming time frame. Every other breath you take comes from phytoplankton, comes from photosynthesis of algae in the ocean. And at 6 degrees C, they can't survive. They can't photosynthesize anymore. And so there's going to be an oxygen deprivation taking place. There's going to be planetary suffocation. 6 degrees C is what we will reach if we continue to release greenhouse gases at the rate that we're currently releasing them by the end of this century. We are on track for 6 degrees C. I hope I've emphasized that enough. The impact of this should not be lost on you. This is an existential issue, right? Our existence and the existence of other plants and animals on the planet are at risk here. And I'll review a couple of papers for you in a few minutes about extinctions, some extraordinary numbers on extinctions. One of the things that a warmer atmosphere does is that it holds more water vapor. And when you have more water vapor, you have drought on the ground. And when it rains, you have intense rainfall. You have torrential rain. So our climate is turning into sort of a bipolar climate. You have long periods of drought, and then you have periods of intense rainfall. When it's intense rainfall, the ground can't soak up that water. And our groundwater reserves, which is where we get our fresh water, are not renewed. They're not recharged. Especially here in Hawaii, at least on Oahu and Maui and Kauai, where a lot of the watersheds, the stream channels have been lined by cement. They've been channelized. When it rains up there in the upper watershed, that rain goes into that channelized stream and it's out into the ocean. We don't catch it. It's not used as this wonderful gift from the sky. And so one of the things that we need to do here in Hawaii to adapt to this problem of changing rainfall is to start to catch stormwater. All over the US, they have stormwater districts where there's a small tax that is paid by the residents in order to put in reservoirs, to build wetlands, other ways of catching water so that we use this wonderful fresh water. Overall, Hawaii rainfall has been declining for 100 years. In the last 30 years, the rate of decline has gotten worse. I think here on the Kona coast, we have seen extensive drought take place over the last couple of decades. This is characteristic of a world that's warmer. Hot areas or dry areas get drier, and wet areas get wetter. And our computer models are suggesting that the rainfall up in the upper watersheds may be stable and may even increase. So the challenge for us to adapt to this changing world of water is to bring that water from where it's being delivered to where we need it, to where we need to use it. And old irrigation systems, et cetera, are a sort of infrastructure to do that. So the United States, some numbers just came out this morning, just had its second hottest year. 2016 was the second hottest year on 130 years of record keeping. It was the second most expensive year for disasters, and we had 15 disasters, each of which was over $1 billion just in the US, for a total of $45 billion in weather disasters we have had. Extreme weather is a characteristic of a warmer atmosphere, and global drought has increased 10% around the entire planet, while at the same time, extreme rainfall has increased 12%. So this change in our weather system needs to be something that we focus on our adaptation efforts. Now the record number of hot days outnumbers record cold days by 12 to 1. So in an unchanging climate, you'd have a normal distribution, but the climate is skewed way over to the hot side, and we have far more heat waves than we do cold snaps. 9 of the 10 deadliest heat waves have occurred in the last 17 years. The thing with a heat wave is that it will park itself over an area for weeks at a time. Everybody runs their air conditioning all night long. The local electricity utility can't provide that much electricity. You start to get brownouts and blackouts. When you get a blackout, for people who live in high rises, the elevator no longer works. The air conditioning for their apartment no longer works. High apartments don't have windows that can open, so your apartment starts to heat up pretty quickly. For the elderly, the infirm, and the extreme young, they can't hike down 20 flights of stairs. If they're living alone, maybe there's no one checking on them. You start to develop fatalities after about 72 hours. They may get on the phone, they'll call the police, the ambulance, the fire. There's only a few hundred of those, and we're talking about tens of thousands of people in urban areas that are experiencing this. If they get to you, it might be weeks before they do. This is exactly what led to huge mortality in Western Europe in 2004. 75,000 people died in the summer of 2004 as a result of a heat wave. In 2010, 55,000 people died of a heat wave in the Moscow area. There are Wikipedia pages on this online. So these heat waves have the potential to be truly catastrophic. They happen now all over the world, and in most of the still developing or underdeveloped nations, you're talking about thousands of fatalities that occur during these heat waves. Today, the Weather Channel reported on how the weather in the continental US is either cold or hot. And it's this bipolarity that's taking place, and I'm going to explain to you why we have this bipolarity in weather on continental scale systems. We now have almost a weather-related disaster every day someplace on the planet. This is an increase of 14% from a decade ago, and it's a doubling of 2 decades ago. And Munich Re, this massive reinsurance company that insures the insurance companies, keeps track of these disasters. They are a statistical, facts-only kind of place, and they and other insurance companies have known about the dangers of climate change long before the media or many other people picked up on this. In fact, here we have from 1980 up to 2014 the Munich Re numbers on loss events worldwide. And the different colors stand for meteorological events, hydrological events such as floods, and climatological events such as droughts and forest fire and heat waves. In red along the bottom there, you have geophysical events. And you can see that that's not increasing because earthquakes and tsunamis and volcanic action are not directly tied to climate change. But the other types of events certainly are. All of our lives are becoming more expensive because we need to pay more insurance. We may not be paying it directly for our own houses, although I believe we are, but everything we purchase rises in cost because basically everything is insured. The ship that brought these chairs here is insured. Everything is insured, and these costs radiate throughout our society. 2016 was a year of historic weather firsts. In West Virginia, there was 1 in a 1,000-year flooding. 4/5 of the state was put under a state of emergency. In Texas, there were 3 major flash floods that broke century-scale records, 1 in a 100-year flooding that killed a dozen people. In California, we had 3,800 wildfires that burned over 110,000 acres. This past summer in the American Southwest, we had temperatures up to 110, 120 degrees Fahrenheit. Those are dangerous temperatures to spend any significant period of time out. And heat warnings went up all over the American Southwest. These temperatures set records in places like Flagstaff and Tucson and Phoenix and Yuma. New England had its hottest summer last year, record-setting heat waves, and its biggest single snowstorm. Snowstorm Jonas was the largest snowstorm on record across the New England area. You can think of climate change as putting weather on steroids. Everything is accentuated. Everything is powered up. Louisiana flooding, another 1 in a 1,000-year event. We had 100,000 people homeless. What do you do with 100,000 people? Suddenly, you have to deal with 100,000 people. You have to feed them, you have to house them, you have to give them water, you have to give them medical facilities. These are huge problems, and our local governments and even our state governments are not equipped to handle these. Even the federal government, when it came to Hurricane Katrina, really stumbled in New Orleans. These costs are rising. These weather records are because of Arctic amplification. So normally the Arctic is very white, it's snowy, it's got a lot of Arctic sea ice, and sunlight comes in, is reflected back out, and doesn't do any work. The sunlight doesn't do any warming. But the warming that's been taking place around the planet, as it leaks into the Arctic, starts to melt the Arctic sea ice, it starts to melt the snow cover, and so more and more of the Arctic now is turning dark. It's dark land or it's dark ocean water. And that absorbs the heat and then re-radiates it as infrared heat. And that's what greenhouse gases trap. So the amount of temperature rise in the Arctic has been on the order of 3.5 degrees Fahrenheit, while the amount of temperature rise elsewhere on the planet has been over 1 degree Fahrenheit, a degree and a half Fahrenheit. The Arctic is warming very quickly. This means that heat from the tropics, where we get most of our sunlight, that is transported through ocean currents and air circulation, as it moves towards the Arctic, is more sluggish, because the temperature difference between the tropics and the Arctic is lessening, the gradient is lessening. And so the distribution of heat is decreased as well. And as heat in the air moves towards the north, the Coriolis effect, the spin of the planet, turns it to the right, and it becomes the jet stream. So here we're looking down on the North Pole. The rainbow is the jet stream. As we turn the planet, we can see the jet stream is a fairly linear body. But as warming takes place, the jet stream slows down and develops these huge meanders. And if you're on the inside of a meander, you're experiencing Arctic air being pulled down, leading to record-setting snowstorms. If you're on the bottom of a meander, you're experiencing tropical air being pulled up, leading to heat waves. And these are called planetary waves. You get 2 or 3 of them on the scale of a continent. And so while on one half of the continental United States it's experiencing a snowstorm, on the other half it's experiencing drought or a heat wave or something like that. In 2012, one of these planetary waves started across the continental US, and it took weeks. And we had the strongest drought ever in the history of the US, stronger than the Dust Bowl. Food prices went through the sky, rainfall collapsed, the food produced in the Midwest collapsed, and we're going to be seeing more of these types of events. Hawaii also had historic weather events last year, largely because of El Nino. On Oahu, we had 11 days of record-setting rainfall. We had 24 days of record-setting heat, so broke our temperature records, and 9 months of drought. This was largely due to the El Nino. Now, you should be aware, you may know, that 2015 and 2016 was a major El Nino year, one of the strongest El Ninos on record. With El Ninos, in Hawaii, you get certain types of weather. You get heat waves, and you saw the record-setting numbers for Oahu. You get extreme rain, again, record-setting numbers. You have a failure of the trade winds. I live on Kailua Bay on Oahu, and I paddle a one-man canoe. And if the trades are strong, I can't take it out. So I look for trades that are 15 miles an hour. If I'm feeling brave, more like 10 miles an hour, then I can take the canoe out. In 2015 and the beginning of 2016, I went out 110 days in a row because there were no trades. This past summer, as the El Nino ended and La Nina has surfaced, we've had a weak La Nina, the trades have returned, and I've only gone out a handful of days this past summer. So a failure of the trade winds means the buildings that we design to take advantage of natural circulation from the trade winds no longer have that natural circulation. And so our architecture doesn't adapt, isn't up to the job during the course of an El Nino. We had 15 tropical cyclones during this El Nino. That's a record. The previous record was 11. The typical number of tropical cyclones in Hawaiian waters is 3 or 4. At one point, we had 3 active hurricanes surrounding Hawaii. That had never been seen before. Large waves. You've heard of the Eddy, right? The great surf competition. Do you realize it was canceled twice because of the waves being too large? We get huge waves during an El Nino because of the heat regime in the North Pacific. And large waves in communities that have built too close to the ocean, which is most of our coastal communities, leads to erosion, flooding of homes, undercutting of roads, etc. Drought, 9 months of drought on Oahu, as I mentioned. The ocean was warmer. The ocean was 2 to 3 degrees warmer during this past El Nino. Warm oceans lead to coral bleaching. And you may have heard that we're going on now our 3rd year of widespread bleaching in the Hawaiian Islands. Hawaii has typically been somewhat immune from coral bleaching because we're in the northern tropics, water's a little bit colder here. We have narrow shelf around the islands, so cold water can come up. Our coral reefs have typically been bathed in cold water, but we're starting to destroy that buffer as we warm the ocean. So all of this happens during an El Nino. Well, the papers you can't read there are computer models from a number of groups that are predicting that in a warmer world, we will have more El Ninos and they will be more powerful. So the science is currently predicting that years like 2015 and 2016, with all those hazards, are what is in store for our future. Knowing this, we can think strategically about our many systems, our economic systems, our housing systems, our transportation systems, our food systems, you name it. All of those systems need to be reviewed and rethought out and re-brainstormed in light of what's going to be coming is regular, very difficult years like the one we just experienced. So, brief reminder to you of what is El Nino. A normal year in the Pacific has trade winds that come out of the southern hemisphere and the northern hemisphere. They tend to blow straight to the west by the time they reach the equator. And as they blow over to Southeast Asia, they push water. And over in that part of the Pacific, sea level goes up. It's a temporary thing. It's related to the normal regime of the trade winds. It actually creates a huge warm pool. There's very warm water there with deep roots, and a lot of heat is stored in the ocean there that would otherwise be in the atmosphere. That warm water evaporates readily, and so you have reliable rainfall that feeds the Southeast Asian monsoon, where the world's rice is produced and food prices are stable during a neutral year. La Nina is where you have trade winds that are especially strong, and we're just now emerging from a moderate La Nina that occurred over the past summer and fall. That pushes an enormous amount of heat over to the Western Pacific. The warm pool is wide and deep, and we get record-setting cold years, right? We get on that, you saw that graph of 130 years of warm and cold. Those cold years tend to be La Nina years. You also get flooding, you get very damaging flooding. Australia had huge flooding in 2009. That was a very powerful La Nina. Food crops tend to be wiped out. The rain is so intense that you see spikes in various forms of economics when you have very strong La Ninas. El Nino is when the trade winds fail. And all that water that was pushed over in the Western Pacific surges back to the Eastern Pacific. And as it passes through Hawaii, it's evaporating, it's warm water, and so we get record-setting rainfall. And when it gets over there towards Central America, it fuels tropical cyclones. That's where our hurricanes and tropical cyclones come from. And with all that warm water, tropical cyclones get invigorated. The warm air means that the wind speed is higher, that when you get a tropical cyclone, it rains more intensely, and we have more of them. So El Nino is all about warm water and where it's located in the Pacific, and the rainfall and the storminess and the drought that results from that. There's our 3 hurricanes Jimena, Ignacio, and Kilo, all around the Hawaiian Islands in the summer of 2015. Here is a map of the last several years of tropical cyclones. Hawaii is right over here. You can see that our storminess originates in the waters off of Latin America. Typically, the hurricanes and cyclones will either fish hook to the north and die off in cold water off of Mexico, or they'll travel to the west. Typically, they'll pass to the south of Hawaii. But we now have observed that this zone is migrating to the north. The zone of maximum wind speeds around the world, at the 5 hurricane centers around the world, is migrating towards the poles. And in the South Pacific, it's migrating towards the South Pole. So Hawaii has benefited in the past from hurricanes passing to the south of us, but now they're migrating to the north, and our windward coasts are more in the crosshairs. And that's one reason why in the last 6-7 years, we've seen more hurricanes. They've actually made landfall here on the Big Island. And what's behind this is this shift in that zone. Another important item is food. You would think that with more CO2 in the air, which is plant food, you'd be able to grow more food. And indeed, wheat and corn and soy and other food crops love that CO2 that we're putting into the air. But the way they love it is they grow thicker stalks and thicker leaves, while the seeds are smaller. So there's actually less nourishment coming out of the plant. In fact, the amount of protein that's provided is less, and the amount of key nutrients like iron is less. So these plants are robust, but they become poor in terms of their food capabilities. Today, global wheat provides 20% of protein to the entire human population on the planet. With rising CO2 and the decrease in the nourishment of this food, by 2050, as the human population reaches 19 billion, the demand for wheat is going to increase 60%, but the actual yield is going to decline by 15%. And there are projections now for a doubling of food prices by 2030, right? That's just 13 years from now. A doubling of food prices as a global average. Well, think about where we are in the world food distribution system. We're at the tail end, right? And the places that still grow wheat and corn and other foods like that, they're going to want to keep the best of those crops for themselves. And what they do release, they're going to really charge a premium price for. So Hawaii is not going to see a doubling, we'll see a tripling or quadrupling. Thus, the mayor's program to increase locally grown food is so very important. We need to become sustainable in feeding ourselves, and not the mayor, the governor. Thank goodness the governor has identified this program. The Sustainable Energy Program that goes back several governors now, that's really doing very well. We need more electric vehicles, but that's doing well. We need the Sustainable Food Program that Governor Ige has announced to also take flight and get wings. Growing our own food is going to be very important. Coral bleaching is happening all over the world. And here is a paper that reviewed warming trends and bleaching stress of the world's coral reefs. So it's warming of the ocean that primarily causes bleaching. Acidification of the ocean, because there's more dissolved CO2, also contributes, but we don't understand the separate roles that they play. We do know that warming is the primary role. And what they found is that the global percentage of bleached reefs tripled over the 28-year period that they analyzed here. And that by mid-century, basically all reefs are going to be dead. 98% of coral reefs will be afflicted by bleaching each year, and coral cannot withstand bleaching with that frequency. Corals don't die when bleaching happens, but if the zooxanthellae that leave the coral don't return within several months, then the coral does die. Our reefs will turn from robust systems of fish and coralline algae to bleached coral and fleshy algae, especially invasive fleshy algae, which outcompetes coral for space on the seafloor. And eventually, once we get up to 500 parts per million, which we will be reaching a little after mid-century, you basically have a sea of weeds. It's just fleshy algae that grows on the seafloor under those conditions. There'll be ghost reefs, remnants of what was once. Sea level rise is one of those big changes that here on the Big Island, you have a much steeper topography. And so sea level rise here is not going to threaten as much inland property as it is on Kauai, Oahu, and Maui. The three sources of sea level rise, roughly 1/3 of sea level rise each, comes from thermal expansion of the ocean as it gets warmer, the melting of Greenland and Antarctica, and then the melting of the world's glacier systems, the alpine glaciers. So each of these is currently driving about 1/3 of the sea level rise that we see happening today. This is the record of sea level rise over the last century or so. At the beginning of the century, sea level was rising on the order of 3 inches per century. During the 20th century, that doubled. It's now doubled again. And over the last 5 years, we're up to 1.5 feet of sea level rise. So the doubling time of sea level rise is shortening, and there's definitely an acceleration in sea level rise taking place. Global average sea level rise. Greenland and Antarctica are both melting. We measure this with the GRACE satellites. GRACE stands for Gravity, Recovery, and Climate Experiment. How's that for an acronym, GRACE satellites? And it's a union by NASA and the European Space Union who have put in orbit satellites that measure gravity. So every time they pass over Greenland, every 10 days, they weigh the Greenland ice sheet. What's the gravitational field created by the ice mass? And it's going down. This is a 10-year record of the Greenland ice mass. And you can see the seasons in there. You can see winter snow and summer melt, and winter snow and summer melt. But overall, obviously, it's a declining database, and it's losing now 281 gigatons or billion tons of ice every year. And Antarctica also, it's more noisy. Antarctica is surrounded by water, so it's got a more noisy weather system, but it's also declining at about half the rate. 118 billion tons of ice per year is melting. Greenland is largely melting from the coastline up. Overall, the entire bank account of ice is in deficit, as I just showed you with that data, but there's still some areas up on the Greenland Plateau in blue that have more snowfall each year than they do melting. But this zone of red, where you have more melting, is migrating up each year 40 meters in elevation, so 130 feet in elevation, but it's now reached the flat plateau. And going up in elevation is no longer an option. It's now going across the flat plateau. And so there's a 50% probability that by 2025, the Greenland ice sheet will go into unstoppable decay. That we will, once we see red across the plateau, we really can't stop it. Unfortunately, we've already reached that point in West Antarctica. West Antarctica is this region facing me. East Antarctica is this massive ice sheet back here. But this region that's turning red has a series of glaciers that are flowing into the ocean. And in 2014, a number of research teams identified that the retreat of these glaciers is unstoppable.
Two groups of scientists reported today, based on close and constant examination, large parts of the western Antarctica ice sheet appears to have collapsed. The area shown here in red, scientists say further degradation is almost certainly unstoppable. They say global warming is accelerating the pace of disintegration. NASA's lead polar ice researcher said, quote, "This is really happening. There's nothing to stop it now." These scientists say the ice sheet can add 13 feet to global sea levels, slowly at first and over the next 100 years or so.
And here's an explanation from Eric Renaud, the lead of the NASA ice team.
We are heading towards a particular sector of West Antarctica draining into the Amundsen Sea. This sector is drained by 6 glaciers. The biggest ones are Pine Island Glacier and Thwaites Glacier. The speed of the glaciers measured by satellite is shown in color code. Red is fast, blue is slower, and green is the slowest. The glaciers flow into the sea and form floating extensions called ice shelves. Now in red are the areas where the flow speed is increasing almost every year. The darker the red, the more the glacier has been speeding up. You see that all the glaciers are speeding up. Now we focus our attention on the Smith Glacier, which is a smaller glacier, but which has experienced some of the most dramatic changes. The grounding line of Smith Glacier in 1996 is at the transition boundary between the blue color, the ice shelf, and the white color, ice resting on the continent. Now we transition to 2011. The grounding line is 35 kilometers farther back, a retreat of nearly 2 kilometers per year. If we could peel off the ice from the continent and see the bed, this is what it would look like. The arrows indicate the flow direction of ice. Their color indicates the speed. Blue is slow, red is fast. We see that the glaciers flow on top of major subglacial valleys colored in brown. The darker the brown color, the deeper the valleys. As the glaciers retreat, they will follow these deep valleys. There is no mountain or big hill along the way that could act as a barrier to hold these glaciers back. The glaciers speed up, the grounding line retreat, the deep valleys that are sloping inland all reinforce each other to make the retreat of ice in this part of Antarctica unstoppable. And we think that this is what is happening right now.
These deep valleys are filled with seawater, and half the melting takes place by warm seawater underneath. The other half is by warm air. So the Intergovernmental Panel on Climate Change, the IPCC, issues every several years a report on the state of climate change. They do not have computer models that assess the retreat of the glaciers, as you've just heard. The computer models are not yet understanding, do not incorporate the physics of the melting of the Greenland ice sheet or the Antarctic ice sheet. Those computer models currently predict 3 feet of sea level rise by the end of the century under business as usual greenhouse gas emissions. When you throw into this the West Antarctic ice sheet and the potential collapse of the Greenland ice sheet, you get up to 6 feet of sea level rise by the end of this century. Now the next IPCC report should be coming out in 2020, a couple of years from now. It will be interesting to see the state of modeling for the ice sheets and to see what their new sea level rise predictions are. We know what sea level rise will look like because of very high waves at high tide today. You get flooding of the land, and sometimes this can be devastating, and other times it need not be. This homeowner has a house that's up on footings. There's airspace under the house. That makes a world of difference. A high wave rushing up onto the property, hitting typical single wall construction in Hawaiian homes, will punch into the living room, flood the house, and you have a total economic emergency. You have a devastating situation for the family that owns that house. That high wave runs underneath the house. It's a source of amusement, right? You hop in your car and you go off to work that day. No real problem. A small difference, a small change in building codes for our coastal zone, so that every building has to have freeboard, has to have some accommodation space, could bring us another generation or two of living in a hazardous area. Our transportation is also largely oriented around the coastline. We have coastal roads on every island. And if we want to build seawalls to protect these, then we're going to lose the beaches that are in front of them. Because a shoreline that is retreating, a beach that is retreating, that comes up against a seawall is a dead beach, right? You lose beaches if you put a seawall in. If you have a land that is made of sand dunes, a retreating beach will still exist. You're giving it the space it needs to still exist. Sea level was 400 feet lower during the last ice age. We had beaches the whole time it rose up to present day. And if we build seawalls, we're going to stop that retreat and we'll end up with beach loss. So my research team at the UH Manoa is interested in what are the impacts of sea level rise, and we model what does 3 feet of sea level rise look like in Hawaii. My research team is led by Dr. Tiffany Anderson. She was born on Kauai. She got her BS in math at UH Hilo and her PhD with me at UH Manoa in the Department of Geology and Geophysics. Shelley Habel is a local girl. She's also getting her PhD. She's modeling groundwater inundation. Because as sea level rises down in the coastal zone, the groundwater will go up as well. Her husband is the captain of the Honolulu Star, the dinner boat that goes out every night. Haunani Kane is an apprentice navigator with the Hokulea. She's led a couple of legs, and she's about to fly off and bring the Hokulea from the Galapagos Islands down to Rapa Nui. So she's going to be navigating that field. She is a PhD student in our group. She went to Kamehameha schools, and she's looking at the connections of Polynesian voyagers related to changing sea level over the last 1,000 years and 2,000 years, because sea level has actually done some crazy things in the Pacific over that time period. Alicia was born and raised on Maui. She's a bachelor's candidate, and her senior thesis is on the impacts of coastal erosion on windward Oahu. Christian also went to Kamehameha schools, and he's a new master's student that we have, and he's studying impacts of sea level rise on beach stability in Waikiki. And Cami, she went to CAM schools, born and raised in Makaha on Oahu. She's also doing a senior thesis as a bachelor's student on impacts of sea level rise on beach preservation. So we are trying to focus on educating local kids, giving them the modeling skills so that rather than heading off to the mainland where they may be from, instead they're from Hawaii. They'll stay in Hawaii, and our local governments, our local industries, NGOs, what have it, we'll have a lot of people with the knowledge to understand what the future we're heading into. We need to have these scientifically trained minds permeate society in Hawaii so that most people are not just left in the dark with a big question mark about what to do. Here is Ewa Beach, Oahu, under 1 foot of sea level rise. You see a little blue shading down there on the Ewa side of Ewa Beach. There may be a couple dozen homes under 1 foot of sea level rise that are inundated by the annual wave. So what we model here is the annual wave that happens every year off of Ewa. Under 2 feet of sea level rise, you're starting to see now on the order of 100 homes that are experiencing inundation. Remember, this will be every year that they're going to be flooded by these summer waves, in this case with the southern exposure. 2 feet of sea level rise is projected by about mid-century, so we're looking at on the order of 30 years from now or so. Here's 3 feet of sea level rise. This is the current projection for the end of the century, but it doesn't take into account the failure of the ice sheets that we've been talking about. Obviously, if you have the whole community up on freeboard, you could still have some people living there, but things are really getting difficult to live here. Roads are getting flooded, and this is only one hazard. There are other hazards related to sea level rise. 4 feet of sea level rise is pretty much game over, and this is a good example of what a lot of coastal communities in Hawaii are going to be experiencing that are on low-lying coastal plains. Coastal erosion, we have a model for coastal erosion as well. And under 3 feet of sea level rise, we're looking at potentially 200 feet of shoreline recession, 200 feet of shoreline recession. And the current state law allows you to build a house within 40 feet of the shoreline. So we're currently permitting houses that will be in a very hazardous situation in the near future. This is Cami's work, her bachelor's senior thesis. Today, in a photograph from 2006 up on Sunset Beach on the north shore of Oahu, we have 20 homes where the shoreline is within 20 feet of the home. And Department of Land and Natural Resources recognizes 20 feet as a place where your home is an imminent threat, and they will consider a seawall application from you. They won't be a done deal, but they will consider it. Now, as we put seawalls up and down the coastline, we are threatening our beaches. Sunset is an iconic beach. It's one of those beaches where we need to really think about what is more important here, the homes or the beach, because our state constitution provides us with guaranteed access to our beaches. By 2030, we're up to 144 homes that are threatened by erosion, that are going to DLNR and asking for seawalls. And if we line this coastline with seawalls, it's Aloha Beach. That's just Sunset. Think of all the other beaches on all the other islands. Most of us think that when sea level rises, it comes across the shoreline, but it actually turns out that probably the worst threat in some places is that the groundwater table rises. This area, Kaka'ako, prior to Western contact, was the #1 salt gathering location in the Hawaiian Islands. And of course, you gather salt when high tide floods the area and then evaporates. So this was already a very low-lying area. And it's only by dredging the reefs and dredging boat harbors that we had enough fill that we raised Kaka'ako and Waikiki about 2 feet. Now, today, 2 feet is about where the water level is at high tide. And this is an archaeology trench going in Kaka'ako for one of the high-rises they're building down there. And you can watch this water fill and drain during the tide. Groundwater is connected to the ocean. And so as the ocean goes up permanently, the groundwater will grow permanently. Salt water also comes up our storm drains. Look at how dry the road is. That's not rainwater. That is salt water that's come up and flooded along the gutter. And that's happening in several locations where we have low-lying infrastructure. When it rains at high tide, there's no place for the rain to go. So that causes flash flooding right in our urban areas. Now here's Shelley's work. Here's the urban area under current sea level. And what you see in yellow is dry soil that's only 1 foot thick. What you see in blue is standing water. Here we are with 1 foot of sea level rise, 2 feet of sea level rise, 3 feet of sea level rise. So that 1 foot of yellow, that dry soil, that's what you need in order to absorb rainfall. And if that's filled, there's no place for the rain to go because the drainage system is also filled at high tide. Miami's been wrestling with this problem already. This is high tide. They call these blue sky floods because it hasn't rained. It's seawater coming out of their drainage system, and they've spent $400 million in pumps and underground storage vaults to deal with this problem. There's Fort Lauderdale, there's Delray Beach, there's Boca Raton, there's Key West, all up and down the South Florida coast. They're already dealing with these problems. In fact, the American Institute of Architects in Florida has now compelled its members, it's required that you design for 3 feet of sea level rise any project that you have. That's the Honolulu Zoo. So we are already looking at some standing water after rainfall that doesn't drain anywhere. We have these problems. All that brown, it's not brown pavement. That's water. That's the Honolulu Convention Center, the Hawaii Convention Center. So this is an architectural rendering of what coastal communities might look like in the future. First, you sculpt the land, you re-topography the land, so you have ridges and swales. And on the ridges, you put robust footings under smart growth. You have buildings that have very few external features so that they can't be ripped off during high winds. Everything is raised above the land surface. And in the swales, you have walkable areas, rideable or drivable areas that are intended to be flooded. There's a French drain running down the middle of that roadway right there. The Dutch, who have wrestled with living below sea level for years, have a saying, and it's if you wage war with water, you will lose. So the rule of thumb here is yield to the water and elevate. So back up where you can and raise. And that is the architectural rule of thumb these days. So let's end with a tour around Oahu. This starts at Kaena Point. The blue is wave inundation. Once a year at the highest waves, under 3 feet of sea level rise. And the red line that you can barely see is the 80% probability of erosion. So that's probably the shoreline. You can see in some areas the waves are flooding. In other areas, the erosion is worse. And the green that you see occasionally, that's where the groundwater table, that's Shelley's modeling, where the groundwater table has risen. What do you call a piece of land where the groundwater table sits on the surface? A wetland. We call it a wetland these days. You know? I know, I was raised with the word swamp too. There we are in Haleiwa. We're looking at some very difficult situations that, if we're ready for them, they need not be costly or dangerous. So I'll end with that, and I think we have a Q&A program.